Welcome to Lesson 9E, Sphere Drag. Today we're going to talk about drag on spheres. This is going to be a little different than usual because I'm just going to copy the clip that I had from ME 405. There's some overlap with that course. In 405, it's indoor air quality, so we look at dust settling in rooms and ventilation, but all the math is the same. So from here, I'm going to just splice in the video that I had created in the fall of 2020 for ME 405. Air pollution particles are spheres, so we're going to talk about sphere drag today. Then we'll look at some various equations that we'll need to integrate into our problems. So let's look at a spherical particle. So this is some air pollution particle. It has a diameter of dp, so p means particle. And let's suppose this thing is moving. Let's just take a case where you have still air. So this is falling at velocity v, but it could be moving in any direction. There's going to be a drag force on this guy, and we'll call that F sub drag. And as you hopefully remember from your fluids class, this is equal to 1/2 rho v squared times the drag coefficient times A. We are going to modify this a little bit when we get to really tiny particles, so keep that in mind. But for now, let's just use this, where A is the projected frontal area. In other words, the particle's coming right at you. So you're looking here from the bottom. What do you see? You see a circle of that same diameter. So the frontal area A is pi dp squared over 4. And then you can calculate the drag force if you know CD, and CD is a function of Reynolds number. Here are some data. This is kind of a famous plot of drag coefficient, CD as a function of Reynolds number. And of course, Reynolds number we have to define. So in all these cases, we have a Reynolds number that's equal to rho v, the diameter of the particle, dp over mu. We're going to call this dp, or since mu over rho is equal to nu, this is equal to v dp over nu. So I just want to take a little bit of time to review what drag on a sphere looks like. There's various regimes. In the first case, if the Reynolds number's below about 1 or so, people call this Stokes flow. There's no apostrophe because his name had an S in it, Stokes. This is approximate here for Reynolds number less than approximately 1, and we're going to actually use, for any analysis, we're not going to use it unless it's less than 0.1 to be better accuracy. At any rate, in that case, CD turns out to be 24 over Reynolds number, which is a straight line on this plot, but you see it starts to veer off like that if you plot a straight line. That's good for very small Reynolds numbers. And then you have between about 1 and 1,000. Between here, we call this the transitional regime. I don't really like that name because it seems to imply transition between laminar and turbulent. It's really transitional between the Stokes flow and what they call a laminar separation region. There's no clear distinction between these various Reynolds numbers, but that's called the transitional regime. And then we get into what some people call up until about 2 or 3 times 10 to the 5th, where you have this sudden change. So we call that the laminar region. And again, that's a misnomer because what happens in this case is the wake is actually turbulent, but the flow around the body that is a laminar boundary layer. And this is between 10 to the 3, 1,000, and let's call it 3 times 10 to the 5th. In this region, the drag coefficient is between about 0.4 and about 0.6, but it's fairly constant in this region. And then suddenly something happens called the drag crisis. Crisis is kind of a strange word. There's nothing horrible going on. It's actually something good, and that is that the drag suddenly drops significantly, and that's because the boundary layer goes turbulent. We don't have enough on this plot, but it eventually flattens out here to around 0.2 or so. And so everything beyond here is turbulent, the turbulent regime. So I wanted to show you some little sketches here. When you're in the Stokes flow regime, the flow is symmetric. So there's our sphere, and you have these streamlines that are exactly symmetric front and back if you have pure Stokes flow. So it looks something like this. This is a highly viscous flow. Once you get into this so-called transitional region above about 1, it's no longer symmetric, but it still has the same kind of look to it, but it'll look something like that. So you start developing more of a wake. This starts to get unsteady, and this is 100. Around 90, you have a laminar boundary layer that separates and it starts to be unsteady. You start to get something similar to a Kármán vortex street, but that's for a cylinder. This is for a sphere, so it's not exactly the same thing. That continues until this next regime, and what happens there is you have the wake starting to be turbulent. So in this region, before the drag crisis, you have a laminar boundary layer, but then you get a turbulent wake. And then finally, when the drag crisis happens, then you get turbulent boundary layer separation. So this is laminar boundary layer separation. When you have turbulent boundary layer separation, far to the right there for these big Reynolds numbers, what happens is the boundary layer is turbulent, so it resists flow separation further. So it goes something like that. So you have a lower drag. As you can see, the drag suddenly drops. Compared to the laminar, it has a much thicker wake. By the way, this is also called fully turbulent in this range. Once it gets fully turbulent, then this drag slowly increases and it levels off around 0.2, as I said. So we don't want to have to pick off things from the graph here. We want equations. Here's a whole bunch of empirical equations for sphere drag. And up till recently, I would always do this with if statements in Excel or any other software. We can combine these into a segmented equations. In other words, piecemeal, where you use if statements. By the way, this first one is Stokes flow here. And that's where I said we're only going to use that if the Reynolds number is much less than 1. It's an approximation, and it's only for very small Reynolds number. And again, so here's Reynolds number for all these equations. CD is just a function of Reynolds number. I wanted to just mention these if statements. So for example, in Excel, if you wanted to put all this in, how would you do that? Let's just suppose we have RE, here's CD, these are just labels in these cells. And then these two cells are the actual values that we want. And let's suppose this is cell B5, and let's just make up a number. Suppose your Reynolds number is 8.8. And what do you put in here in order to get this combination of equations? You have to use if statements. So here's how I would do that. I would say equal if, and then I'm assuming that this is cell B5, so you click on that cell, it'll put a B5 there, which it has the value of 8.8, but in the equation it'll look like this. If B5 is less than 5, so we're taking this first equation here. Ignore this one. We're not going to use this one, just as a quick approximation. So we're going to use these. So if B5 is less than 5, we want to use this equation. So then I put that equation, comma, 24 times 1 plus, and then you just put in the equation, 0.0916 times Reynolds number, which again is B5, parentheses closed, divided by B5 because of this Reynolds number in the denominator. And then I put a comma. So how this works is if this is true, then we do this. So if Reynolds number is less than 5, we're doing this equation. And then this is if it's not true, if it's false, we could just put something else. And in a nested if, I will put another if. So if it's not less than 5, then I'm going to say if B5 is less than, now 1,000 for the next equation, comma. So if this is true, if B5 is less than 1,000, we want to use this third equation on my list. So I would put 24 times 1 plus 0.158, etc. And at the end, you have to close all your parentheses. We're going to do another one here. So this is how I always used to do this. By the way, this is called a nested if statement. And if you're interested, if you've never used this before, this comes in very handy in Excel, not just in this course, but anywhere else you need it. By the way, I have a YouTube video that shows you how to do these nested ifs in Excel if you're interested in further details. That's all fine, but there's a big problem with this. This is how I used to do this before I changed recently, and that is that the segmented equations, there are discontinuities. Everywhere you transition, so if the Reynolds number is less than 5, we use this equation. If it's greater than 5 but less than 1,000, we use this equation. So there are transitions at 5 and 1,000, and then if you keep going with higher Reynolds numbers, you'd even have more. The segmented equations is this black line. Digitized experiments follow that dashed line. Stokes flow, the 24 over Reynolds number, is this kind of orange line. What I wanted to point out was there's a discontinuity at 5 right here. You can barely see that one. That's not a very large discontinuity, but the one at 1,000 is huge. This is a discontinuity. There's another one if you stop at 2 times 10 to the 5th, and then you make it 0.2 from then on. So it follows the data fairly well, but there's these discontinuities. And what happens is you can get into infinite loops where you're trying to converge on things and it's bouncing between right after this discontinuity and right before the discontinuity, and it just never will converge. So we had issues. And so this is not a very good way to do the segmented equations with all these ifs. So fortunately, in 2016, there's a professor, Faith Morrison, who figured out a curve fit for all the Reynolds numbers below 10 to the 6th. And here's her equation. It is a big, long equation, but what's nice about it is it's explicit. There's no iteration required, and it's accurate. It matches the data pretty well, very well. And I just want to put lots of stars around here and say, in this course, we will always use this Morrison equation for CD. The only exception is when we know we have really, really small Reynolds numbers. And I say 0.1, but if you have 0.0038 or something like that, 24 over RE is going to give you a really good approximation. And it's much simpler to just plug that in. But you can see that her equation has the 24 over RE in it, and then it just has all these other correction terms to get the whole curve. And here's a plot, the same plot, but now I added Morrison's equation, which is this red line, and you can see that it follows the data. Even the drag crisis, it does almost perfectly, and it starts to recover to the 0.2. So this can be used for all Reynolds numbers below 10 to the 6th. This is a million, or 10 to the 6th right there, all the way down to any low Reynolds number you want. This will just continue up like this, straight line on a log-log plot like this, as far down in Reynolds numbers as you go. So this will be our workhorse equation, and I just wanted to show you how it compares with Stokes. I did these calculations, and by the way, you should verify these. Make sure you know how to use the Morrison equation. Program it into your favorite software. So let's just list Reynolds number and CD for Stokes and CD for Morrison. So let's start with a very small one like 0.01. Stokes is trivial. You can do this in your head. 24 over 0.01 is Stokes, just that first term. So that gives you 2400. What does Morrison give you? It gives you 2400.15. So it's really, really close. We never give things more than about 3 significant digits for it, the very most. So we're in good shape for a very low Reynolds number. 0.1, you get 240, and Morrison gives you 240.22. So that's why I say below 0.1, Stokes flow is a very good approximation. At 1.0, we get 24. Now here we get in Morrison 24.673. So you can see you're starting to get some error in the second digit. So we round that to 25 in 2 digits. So you're starting to get some error. And the bigger the Reynolds number gets, the more there's error. So Stokes would be 2.4, just 24 divided by Reynolds number. And this turns out to be 3.9676. So that's not a very good approximation. We would say never use Stokes beyond this Reynolds number of about 0.1. However, you can use it for a quick and dirty approximation when the Reynolds numbers are small, even around 1. But we're going to use this equation as our workhorse, as I said. So what I want to do now is an example. This is a simple example, but you got to put this equation in to your spreadsheet or MATLAB or whatever software you use. So let's take a quick example, 1.5 millimeter sphere moving at a speed. The air properties are given, rho and nu. I gave nu in this case. Remember that nu is mu over rho. Sometimes you need to get nu out of mu or vice versa. And all I want you to do is calculate the Reynolds number and the drag coefficient for this sphere. So here's the Reynolds number and Morrison's equation. So let's start with the Reynolds number. I put in my 1.25 meters per second. From up here, I put my 1.55 millimeters, and I put my kinematic viscosity. I didn't really need the density in this problem because I had kinematic viscosity. And then I need a conversion factor so that Reynolds number has to be non-dimensional. So since I had millimeters, I used this unity conversion factor. And then you can see I have 2 meters there and a second in the bottom on each. So this all turns out to be 135. I'm going to give you a few extra digits here. We're going to put that into our Morrison equation now. So this is the Reynolds number, which I asked for. And I should have said using Morrison, which I have here. So now calculate CD, and I am not going to write that all out. In fact, I am not going to do that with my calculator. put this in Excel, MATLAB, whatever software you use, and put it in once. Do it carefully and make sure you can generate this column, these values, using Morrison's equation for these Reynolds numbers. And also for this particular example problem, plug in the speed and the nu and the particle diameter and make sure you get the same Reynolds number. And then make sure you get the correct CD. I'll give you the answer, and do this before you try the quiz. You need to make sure you get this right, and then everybody should get 100 on the quiz, because I'll tell you right now, the quiz is just going to be very similar to this problem. You calculate a Reynolds number, and then you calculate CD using Morrison, and I'm going to ask for 4 significant digits to make sure you're doing this correctly. I'm going to quickly show you in Excel, which most of you are using, and Excel is very good for these kind of things when you have to do lots of different diameters later. Let's suppose we have a cell for RE and a cell for CD. Suppose that you put in a number, and now I'm going to put this number as 135.869. And let's suppose this is cell number B5. What do I do here? I want to get CD. I'm going to write that out as equals, and no if statements here. I'm just going to put 24 divided by Reynolds number, that's B5. So I'm just doing this equation, that's that term, plus, following that equation, 2.6 times Reynolds number, B5, divided by 5.0, and then close both parentheses. That gives me my numerator. And now the denominator, you got to be very careful with parentheses in Excel. So we want Reynolds number over 5.0 to the 1.52 exponent. I'm going to put 2 parentheses, B5 divided by 5.0, close parentheses, and then the little hat gives you the exponent of 1.52. And then I'm going to close that parenthesis. You need to close the third one as well. And then you're done with that whole denominator and that whole second term plus, and you got to do this carefully for the other terms. So we got these first 2 terms. I showed you how to do that. The other ones are similar. Do the rest of the terms. Put this in, and once you have this, as long as you have the Reynolds number and CD next to each other like that, so Reynolds number to the left and CD to the right in your Excel spreadsheet, so always put it in that way, then you can simply take this and copy and paste into some other region where you have a Reynolds number and a CD in 2 different cells like this. You can paste that right into here. You can also in Excel get that little square and fill down. It'll automatically point, instead of B5, it'll point to the next row. So that'd be B6. I can't emphasize this more. Do this problem in whatever software you want. I'm assuming you're using Excel, but people like MATLAB and other things. Whatever you use, put it in. All you have to do is type this in once, because you're going to copy and paste it from then on. Get my answers. If you're confident with that, take the quiz, and everyone should get 100% on that. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.